binding energy and mass defect. The total mass of a nucleus is always less than the sum of its constituent neutrons and protons. So where has this mass gone? It has become energy, such as radiation or kinetic energy. In other words, when a nucleus is put together, you've got a certain mass of neutrons and protons, you put it together, energy is released, because the mass of the combined protons and neutrons in the nucleus is less. Where did that mass go? It had to go somewhere because of the conservation of mass energy. In this case, it goes to energy. So we have a definition here. The total binding energy, remember we just talked about putting a nucleus together, so the difference between the total mass of the individual nucleons, the individual protons and neutrons, and the final mass of the nucleus is called the total binding energy of the nucleus. In energy units, the total binding energy is given by E sub B for binding energy, delta M, where this delta M is the mass difference, times C squared. In words, the binding energy is the amount of energy needed to be put into the nucleus in order to break it apart into protons and neutrons. Let's show an example as to how to calculate the binding energy of an isotope. We're going to start with boron 10. And notice I just say boron 10 because the 5 here, which tells you how many protons there are, only boron has 5 protons, so that's somewhat redundant. We have 5 protons, 5 electrons, and 5 neutrons. Now, for our calculations, we're going to use the mass of the hydrogen atom for every proton we have, because when we're subtracting out the mass of the boron isotope, that includes all the electrons, and even if they're small, it is a factor. So we will be using the hydrogen atom when we talk about how many protons we have. That'll become clearer hopefully as we do the problem. So the total mass here, we have 5 neutrons. They have an atomic mass unit. Each neutron weighs or has a mass of 1.008665 atomic mass units. The hydrogen atom, which is a proton plus the electron, is 1.007825 atomic mass units, and we have 5 of them. And the mass of boron, which includes 5 neutrons, 5 protons, and 5 electrons. So you can see by using the hydrogen atom, we will subtract out the electrons so they won't come into the problem. So we will find the mass defect. We have over here, here's the 5 neutrons. You can see 5 times the mass of the individual neutron. We have here the hydrogen atom, which includes the proton and the electron. And then here's boron, and there's just one of them. And again, this has 5 neutrons, 5 protons, and 5 electrons. And we get a mass defect of 0.069513 atomic mass units. So that shows that the individual constituents that made up this isotope have a greater mass than the boron isotope. So where did that mass go? And that will be shown on the next slide. The neutrons and the protons weigh more than the nucleus that is put together from them, and that missing mass is converted into energy, which is the binding energy. So the binding energy is either how much energy you need to break it apart, or it's how much energy which is released when you put the neutrons and protons together to make a nucleus. So we need to convert the mass defect that we found on the previous slide to either kilograms or this other unit. And now we're going to see why this sometimes is more convenient to use, and certainly for nuclear physics it's more convenient to use. We have, this is how many kilograms there are per atomic mass unit, and then we have 931.5 MeV divided by C squared per atomic mass unit. So we have 2 mass defects here. One is in kilograms, one is in this other slightly more unusual unit. We then find the binding energy from Einstein's formula, E equals mc squared. So we substitute in, if we want to find the energy in joules, we use this term here, the kilograms, times the speed of light squared, and we get 1.0388 times 10 to the minus 11th joules. If we want it in MeV, we take this mass defect, and you can see the math is quite a bit easier. We have MeV per c squared times c squared. These guys just cancel each other out, and we're left with a binding energy of 64.75 MeV. So the math is easier, and it's a little easier to say when you're working with nuclear binding energies than worrying about joules and kilograms. What is the mass defect and binding energy of potassium-40? And here's potassium-40, here's its mass in AMU, and here's some other masses in AMU of a neutron, a hydrogen atom, and potassium-40. And the hydrogen atom consists of 1 proton and 1 electron. So we have our atomic mass number of 40 and charge of 19, which means there's 19 protons. So we have to find the number of neutrons. That's going to be 40 minus 19, so we have 21 neutrons. And we have 19 proton-electric pairs. Now that's important why we said the electron pair there, and you'll see on the next line. Here's our binding energy equation. Number of neutrons times the mass of a single neutron plus the number of protons times the mass of the hydrogen atom. That will enable us to subtract out the number of electrons. And where is that coming from? The mass of the isotope includes the electrons. We don't want to deal with electrons here when we're talking about the nucleus. So here's our number of neutrons, mass of the neutron, number of protons, mass of the proton-electron pair or the hydrogen atom, minus the mass of the isotope, potassium-40. So here's our mass defect right here in atomic mass units. To find it in MeV, we use a conversion factor. So here's our atomic mass units. There's 931.5 MeV per c squared per atomic mass unit. So these cancel, and we get here is our mass defect. Now, this is the exact same number as this, but just in different units. So let's continue on the next slide. To find the binding energy, we'll use the mass energy equivalence formula. Of course, this is Einstein's formula. And we found delta M on the previous slide, and we converted it to MeV over c squared. Why did we do that? Look at that. We multiply by c squared from Einstein's formula. C squares cancel out, and we get a binding energy of 342.5 MeV. Even though the mass and energy have the same numerical value, they are different because of the units, right? This is an energy, and the mass defect is an MeV per c squared. An interesting result is obtained by plotting the binding energy. Let's get the pen here. The binding energy per nucleon. So we would take the entire binding energy of the atom and divide it by how many protons and neutrons there are, and that will give you binding energy per nucleon. And we'll plot that on the y-axis, and then we'll plot the nucleon number on the x-axis. The curve will follow, but let me just talk about this here. The curve will peak at iron 56. That's what most textbooks say. New research suggests that the peak is at nickel 62. Again, that just shows how physics is continually changing as new work is done, new experiments are carried out. There's structure in the curve below that mark due to the energy levels of the different nuclei. Helium-4 has a relatively high binding energy per nucleon, and that indicates that it is very stable compared to the nucleons right about it. So again, just a reminder of binding energy. That's how much energy you have to put in to protons and neutrons to put them together to have them form a nucleus. Now, nuclear binding energies, which is what we've been talking about, are on the order of 1 million times greater than electron binding energies. It's very easy to rip electrons off of atoms. We do it all the time with static electricity. However, with the nucleus, 1 million times more is the energy required, and that's why nuclear reactions involve so much more energy than chemical reactions. Here's the curve of binding energy per nucleon, and that's right over here on the y-axis, average binding energy per nucleon in MeV. And here are the number of nucleons in the nucleus, atomic mass number A. And you can see how the curve goes up very sharply here, more and more energy, okay, to remove one nucleon. That's basically what it is, how much binding energy you need to kick out one nucleon, whether it's a proton or neutron. Here's the peak at helium-4. So helium-4, compared to its neighbors, has a very high binding energy because then it goes right down here. That means helium-4 is very, very stable. The curve keeps rising right up to around the iron-nickel area right here, and then it decreases. And on the next slide, we're going to talk about what it means for the binding energy for nucleon to be rising up until it gets to this point, and then it steadily decreases the more massive elements we talk about. The significance of the binding energy per nucleon curve, remember, it kind of rose like this. I'm leaving out helium, and then it started going down right after nickel, around nickel area, iron, etc. And helium peaked here and then came down. Elements to the left, okay, to the left of iron 56, are created in stars using a fusion reaction. More about that later. But basically, you have nuclei are combining to form a larger nucleus, starting by combining hydrogens into helium, which is the main reaction our sun uses to release energy, and that will release the binding energy. So that's fusion. So to the left of that line, you have fusion reactions. These reactions release more energy than is put into the reaction, and that's what causes our sun to shine. Elements to the right are created in the last stages of a star exploding, or supernova. That's because they release less energy than the energy required to fuse smaller nuclei. And the only way you can get enough energy to put these elements together, to the right of nickel, to the right of iron 56, is by a supernova explosion. So the heavier elements all came from stars exploding. The lighter elements were created as a star was going through its life cycle. Although the heavier you get, the closer you get to iron, a lot of those elements were formed just in the first few seconds of the supernova explosion.